Hello everyone, welcome back to our channel. Today in this video, we're going to discuss time-related rates. If the value of a variable x is dependent on time t, then we can say that the rate of change of the variable x with respect to time t is equivalent to dx all over dt. This is called as its time rate, or the rate of change with respect to time. Now, if two or more variables are related by an equation and each of the variables depends on time, a relation among the respective time rates may be obtained by differentiating the given equation with respect to time t. So there are rules to follow and we're going to discuss them one by one. Number one is to find an equation involving the variables, which is always true for any time t. And number two, we can now differentiate the equation with respect to time t. And number 3 is determine the unknown time rate from equation 2 using equation 1 if needed. So let's have some examples. A kite at a height of 60 feet is moving horizontally at a rate of 5 feet per second away from the boy who flies it. How fast is the cord being released when 100 feet are out? Alright, so let's try to illustrate it, and here is where we'll start our solution. So one might guess that it's actually in a form of a right triangle, wherein 60 feet is the height above the ground and 100 feet is the length of the cord. Okay, and then we have the 5 feet per second, which is the rate at which the kite is moving away from the boy with respect to the x-axis. Okay, so we can now find the leg of, or the missing leg, using the Pythagorean theorem. So we see that b squared, or the base, or the x here, is equivalent to 100 squared minus 60 squared, and take the square root of that, and that is 80. We'll let y to be the length of the hypotenuse and observe that after reaching 80 feet, okay, this is only the time when we are asked to find the rate of change of the length of the cord, or the rate at which it is being released or rolled out. Okay, so we're going to write y squared is equivalent to x squared plus 80. Okay, so suppose that the rate of change is in small enough, okay, and this equation would be accurate. Okay, so at that instant 80 point something, 80.111, okay, I think that the equation is still logical. Okay, so this is our equation. That's step number 1. So step number 2 is to differentiate. Okay, so dy dt. Okay, so the derivative of y squared and the derivative of x squared with respect to the rate of change in the value of time is 2x and 2y respectively. 2y is equivalent to 2x. We divide both sides by 2, and we can write this equation as y times dy dt is equivalent to x times dx all over dt. And with the knowledge that dx all over dt is 5 feet per second, we can solve for this equation by just dividing both sides by y, and we can find dy all over dt is equal to x all over y times 5 feet per second, which is equivalent to 80 times 5 all over 100. And then we're gonna get 4 feet per second. Okay, so that's the rate of change at which the cord is being released along the hypotenuse, or the line of sight of the hypotenuse.